Let's look at some exponential growth and decay examples using differential equations. So it says oil is pumped continuously from a well, so that would be like leaving decay, at a rate proportional to the amount of oil left in the well. Initially, so the initial amount, there were 1.1 million barrels of oil. 6 years later, 500,000 barrels remain. At what rate was the amount of oil in the well decreasing when there were 600,000 barrels remaining? All right, the differential equation for this is a value that is proportional to the amount that the quantity that's there. Okay, so remember the Q is a function, the quantity at a particular time. This is negative, of course, because it's leaving the well. All right, so the solution to this differential equation is given by the quantity equals CE to the negative KT. So if we go through the steps to try to solve this, it says initially, well, initially is when your T is 0, so anything to the 0 would be 1. So initially, the C would be 1.1 million barrels. And then it says 6 years later, so where you see T, go back, there was a T here. You're going to plug in 6 years later, this equals 0.5. So they're asking what the rate, which is this left-hand equation here. So this is what we actually need. But over here, notice I have an equation now that has every single part in it, every variable except K, so I'll be able to solve for K. So looking for the rate, once again, I need to know K, so I'm going to have to work this piece over here and solve this for K. So to be able to do this, we've worked problems like this. There's many steps, right, in between here where you can kind of see what the steps are. The first step is take 0.5 and divide by the 1.1. So that piece gets moved over there. Then the next step is you have your e to the negative 6k, basically. So you natural log that piece to bring that down. Then you divide by negative 6 and you get your value of k. So once you have your value of k, you can plug this in here for the rate and then times 0.6. Notice that this stuff was given, go back here, in millions of barrels. Oh, so if we're at 1.1, 500,000 is why we're using 0.5. And then the same thing with 600,000 using 0.6. So this is saying the rate of oil is decreasing in about 78,846 barrels per year. All right, and of course decreasing because of the negative sign. So this is a solution to a differential equation that's using decay, leaving, in this case, the negative K value. All right, let's say we have something just like the last example, but instead of just one rate out, we also have a rate going in. So a patient is given a certain drug, okay, this 43.2 milligrams per hour to relieve acute asthma. The rate at which the drug leaves the patient is proportional to the quantity that's there with this proportional constant. Assume the patient's body contains none of the drug initially. All right, so I have this information. What we want to do is set up our differential equation where this is a rate in minus our rate out, and the rate out is going to contain the actual quantity that was there. So my rate in, 43.2 milligrams per hour, my rate out, negative 0.082, times the quantity that was present at that time. Now, this is a different solution to this differential equation. This differential equation with rate in minus rate out is given by this on the left. Now, what we have to do, we have to make what's on the right look like this. Well, that's easy because you just factor. How do you factor? You divide. So I'm going to divide negative 0.082 out of every single term. So If I take negative 0.082 and divide it on this term, that's where Q comes from. If you pick your calculator up and you take 43.2 divided by the K, negative 0, because that's what's getting factored out, you will see where that number came from. And so now notice here with this example that this is the solution. All I have to do is see, okay, K, negative 0.082, A, 5.26.8. So I have everything that I can plug in here. So I plugged in my A, 526.8. I plugged in my K. Now you were told initially the patient has no drug in their body. Well, think about what that would mean. Initially is when T equals 0, e to the 0 is 1. So these two numbers have to match, where of course this has to be negative. And this shows, how you could solve it. But just by logic, these two numbers have to be opposite for the quantity to, in the very beginning, when T equals 0, for the quantity to equal 0.